welcome back to StudyOnion, and today we're going to be talking about Aristaurchus and Eratosthenes. Let's get started! So, Eratosthenes has been attributed with the original calculation on the circumference of the Earth, and he basically went through these steps. He noticed that on June the 21st, which is the date of the summer solstice, at noon, the sun lay directly overhead in the city of Syene. This meant that no stick and no column of a temple would form a shadow. At the same time and same date on Alexandria, which is further north a little bit in Egypt, a stick did form a shadow, and this kind of suggests that the sun was not directly overhead and was at an angle to Alexandria. Now, from this, Eratosthenes sought to find the angle between the sun and the vertical, and I'll put up a diagram that explains a little bit more in just a second, but he measured basically the height of a pole that he put in Alexandria and the length of a shadow at noon. Now, with these two measurements in hand, he basically said that tan A, or of the angle that's on that diagram right there, is equal to the opposite divided by the adjacent, as we already know, which is also equal to the length of the shadow at noon divided by the height of the pole. And he did this to find angle A. And from this angle, he was able to draw a second diagram, as you can see to the right. And what this diagram is basically showing is that while the sun was directly overhead in Syene on June the 21st, it was not directly overhead of Alexandria, and I've labelled angle A on here so that we can compare the first and the second diagrams. And he basically said that angle A was alternate to angle B, and because alternate angles are equal, he was able to calculate that angle B was around 7 degrees. Now, he used this angle that he found of around to create a ratio, as we can see right now. And he basically said that the distance of the circumference of the Earth divided by the distance from Syene to Alexandria would be equal to 360 degrees divided by 7 degrees. And where this 360 degrees comes from is that a full circle around the Earth is 360 degrees, and we've already measured that the angle between Syene and Alexandria is 7 degrees, and he used this to calculate the circumference of the Earth. Now, he somehow actually measured the distance between Syene and Alexandria. We're not exactly sure how. There are lots of different theories, but all in all, he got a value with plus or minus 2 to plus or minus 20% of accuracy in his calculations. Now, while the measurements weren't the most accurate out there, what this meant is that this method could be used to find the circumference of the Earth. Now, if we look at Aristaurchus, he has been attributed to the original calculation of finding the diameter of the moon, and he did the following things. He looked at the relative motion of the Earth during a lunar eclipse, and this is when the moon isn't visible or is being covered by the Earth, so isn't getting direct light from the sun. He firstly made an assumption that the Earth's diameter was equal to its umbra, and the Earth's umbra is the shadow that the Earth casts behind the Earth. He then decided to use 4 positions of the moon as it passed through the Earth's umbra, as shown here. Now, this dotted line is used to show the path of the moon, and it starts at U1, moves to U2, U3 and U4, and we refer to these as the points of umbral contact. So U1 is the first point of umbral contact, U2 is the second point of umbral contact, and so on and so forth. Now, what this basically means is that Aristaurchus knew that since the moon travelled at a constant speed for the duration of an eclipse, he could use time intervals between these 4 points to calculate the relative sizes of the moon and the Earth. Now, the time interval U1 to U2 or U3 to U4 is the time it takes for the moon to travel the same distance as the diameter of the moon. And if you're looking at this diagram, it's best to pick one point on the moon and follow it across to see how that makes the diameter of the moon, rather than looking at where the positions of the two moons are exactly. Now, the time interval U2 to U4, or U1 to U3, is the time it takes for the moon to travel the same distance as the diameter of the Earth. And this led to creating this ratio of time intervals. So the diameter of the moon divided by the diameter of the Earth is equal to the time interval between U1 to U2 divided by the time interval between U2 to U4. And if we combine this with Eratosthenes' value for the circumference of the Earth, and hence we're able to calculate the diameter, we can work out the diameter of the moon. Aristaurchus then wanted to calculate the distance to the moon, and when he held his thumb at arm's length, he reckoned it was just able to cover the moon's disk, as shown in that diagram. Aristaurchus first tried to work out the angular size of his thumb, and this is the angle between the distance and the diameter of the moon. To do this, he measured two things. He measured the length of his arm and the width of his thumb, and he said that tan theta equals opposite divided by adjacent, which is equal to the width of his thumb divided by the length of his arm. And by doing this, that angle would be equal to the diameter of the moon divided by distance to the moon. And this is basically the same thing as the angular size of the moon. Now, to work out the distance to the moon, we only used half this angle because the distance to the moon is actually only up to the midpoint or the center of the moon and not right up to the edge. Now, you see this diagram here to explain this a tiny bit further. As we already know the diameter of the moon from the previous calculation, we can work out the distance to the moon using tan half theta equals radius of the moon divided by distance to the moon, and then we can rearrange this to create distance to the moon equaling the radius of the moon divided by tan theta. He then decided that he wanted to calculate the distance from the Earth to the Sun. And to measure the relative distances of the Sun and the Moon, Aristaurchus completed some measurements when the Moon was at first quarter, and this is when the Moon looks like this. Now, Aristaurchus measured the angle between the Sun, Earth and Moon, knowing that at first quarter, the Sun-Moon-Earth angle is a right angle. We're not exactly sure how he measured this angle, but he measured a value of 29 by 30 of a right angle, and that is equal to around 87 degrees. Although trigonometry was actually yet to be invented when Aristaurchus did these calculations, we can use it now to demonstrate the ratio of the distance to the Sun divided by the distance to the Moon. So cos theta, which is equal to adjacent divided by hypotenuse, where we can write this as cos theta divided by 1 is equal to the distance to the moon divided by the distance to the sun. And if we flip these by multiplying both of the sides by -1, 1 by cos theta equals distance to the sun divided by distance to the moon. And then we substitute some values in. And if we substitute his value in, we actually get 19.1 moon distances, which is equal to the sun distance. And this means that the sun is actually, if we did these calculations with the right values, we would get that the sun is about 400 times further away from the Earth than the moon. Obviously, Aristaurchus' values were off because he got 20 moon distances. However, we actually can do this exact method today and get the correct value of 400 times further away from the Earth than the moon. We actually now know that the sun is 400 times bigger than the moon and 400 times further away. And this actually means that the moon and the sun subtend the Earth on equal angles. So, to summarise, Eratosthenes calculated the circumference of the Earth using the height of his pole and the length of the shadow that it cast during the noon. He found that angle A and angle B were alternate angles and used this to find the circumference of the Earth. Aristaurchus went on to find the diameter of the moon using the path of the moon during a lunar eclipse. He basically found that the diameter of the moon divided by the diameter of the Earth is equal to the time interval from U1 to U2 divided by the time interval from U2 to U4. Aristaurchus then went on to calculate the lunar distance by working out that the tan theta, which is opposite by adjacent, would be equal to the width of his thumb divided by the length of his arm, which is also equal to the diameter of the moon divided by the distance to. He then continued and found that the distance to the moon would be equal to the radius of the moon divided by tan half theta. Now, he did measurements at first quarter to find the solar distance. He found that the angle between the sun and the moon at the first quarter phase is 87 degrees, but the angle, the sun-moon-earth angle, is 90 degrees. Found that cos theta would be equal to adjacent divided by hypotenuse, so cos theta by 1 would be equal to the distance to the moon divided by the distance to the sun. Therefore, 1 by cos theta would be equal to the distance to the sun divided by the distance to the moon. Finally, we also found that the moon and the sun subtend at equal angles from the Earth's perspective. Hopefully that helps you learn more about sizes and distances that were calculated by Eratosthenes and Aristaurchus. See you next time. Bye bye!